Testing, testing, and waiting for someone to pop in, perhaps, confirm. Testing. Cool. And probably not going to wait. Let's see. So I wanted to do a video today on kinetic energy, oil canning, tin canning. And let's see if I can do this. Let's go back to the shared screen and screen share. And I'll show you what I have going on. I'm just waiting to see if it catches up for shared screening. Good. So Mark wrote me again. Mark, I didn't finish reading this. I don't take on arguments. I don't even read arguments. Sorry that when you lose me, and you lost me pretty much in a couple of stages back, and I'll explain why. But interesting enough, I did glean over this, and then I stopped, and I saw you said kinetic energy. That's what I've been working on just now. The tabs here. You wrote this 23 minutes ago. The tabs here. I was working on kinetic energy, and I'm actually going to show it because I was going to do a video with DY Auto School, this guy here talking about tin canning, and it's going to taper into your kinetic energy, into the structure of the bridge also. If you can understand kinetic energy and equilibrium and hinging, and you'll understand so much. So I'm going to show for excitement here. Let's do this first. He calls this tin canning. It's actually oil canning, and then we'll go from there. Let's hear him.
Because when you're working on a piece of sheet metal this long, it's very, very important to make sure that you don't warp the panel. Now, I want you to pay close attention here when look how I'm pushing in on that.
So what is he doing? He's applying a load. With the load, he's creating, to help you guys understand it, I try to simplify things, he's creating a hinge somewhere, and that's what we call a moment. All right, so think of a moment as a hinge. It's creating a hinge somewhere, but we may look at it here, but realize he created a load, and it's not just there. It's everywhere around, from this point load to everywhere. Just because you can't see it doesn't mean it doesn't exist. He applies a load to the point that he can see it. So right now he's applying a load on the floor. This is applying a load on the floor. They all are finding equilibrium. This trunk is up. It's found equilibrium. The springs in here are counterforcing the hinge from wanting to fall down because of equilibrium of weight, not gravity. All right, let's just throw gravity out the window. I don't believe you should add it into any formula dealing on the Earth. And maybe you can add it going into space if you believe in gravity. All right, so you can say what you want to say, but gravity can't be proven. So you can't just give me an imaginary force and tell me I should add it to a formula and give me a calculation of a factor to use this imaginary force. Because first you got to prove the gravity. The apple falling out of a tree is just finding equilibrium. It's holding on to the tree, but the growth through the stem. The apple through nature, where it's now matured enough where it no longer is alive. The weight of the apple can no longer be maintained by the stem. The stem and the tree connection is what's coming in tension. That's what fails. It's not gravity pulling the apple down. The gravity is not pulling anything down. All right, gravity it's ridiculous. Everything's in equilibrium. And if you look this up, it's quite some argument with this. But let's go with equilibrium, because if gravity's with everything, when he pushes this in, what part of gravity's participating in this? Because clearly he's changing gravity by pushing this in. So I could argue that gravity is now pulling on the void he created at the top of this dimple, and gravity wants to fold this thing up into fold it up like a hinge, right? Just fold it around his hand now. That's a ridiculous statement.
And take for granted now, this is a 67, so the sheet metal is not paper thin like it is today. And I want you to see where I'm pushing it in. you hear that? That's called tin canning.
I stop right there. So I found you for this video was supposed to be about oil canning, not tin canning, as he stated. So I wanted to help him out, saying it's called oil canning, and help him understand what's going wrong with his. And he doesn't take help like this very easily. I helped him, gave him some data on his concrete ones, but over auto body, of course, he's considered he's an expert, right? He's been doing it so long, I would consider him an expert. Just a little refining some of his knowledge. That's all. If you looked at my other video I did on my other channel, Eric, with if you guys go there, Texas Barnuminium. I support other channels, guys. I'm not jealous of anybody. Envious, but not jealous. So I support other channels with that in mind. I know my biases. So what's great about Texas Barnuminium, if you look at my other channel, he's realized that all these years he's got some stuff wrong, and now he's willing to change, or he's growing. And if the last video I made shows how he talks about it, you can hear him psychologically talk about how he made the mistake. It's about growing. Don't believe gravity. All right. So gravity is my number one pet peeve, as far as it's a trigger for me. Let's jump into this is oil canning. This is what it looks like, and it's dealing with stresses. I'm going to give you these links here. How to prevent oil canning. It's your ribs. You know, your counter forces is what it amounts to. The sun can be doing some of the wrinkling, your placement of the screws. Here's kinetic energy. This is the most beautiful thing there is. They tie kinetic energy and potential energy together frequently. To me, that's like tying a punch and a non-punch together. You can't tie a non-punch with a punch. One's a punch and one's a non-punch. All right. So I'll troll myself this morning into videos, into part of my thing. And this guy, he had me until he went over here and started talking about gravity, how he's going to do this pendulum. So let me write down a note here, 206. And so I don't throw out the baby with the bathwater. So I like his content, but I throw out the part about gravity. And let's go here. And I might be trolling you guys. You might be really upset because you really believe gravity is participating. It's equilibrium is all it is. Everything's finding equilibrium. And I'm going to show you, you know what? Before we start this, let's start this, and then I'll show you in the background what I'm doing. So if my man's here, he thinks I'm pressing a pen. I am not. You guys, it is going to show equilibrium. Oil canning also. Here we go.
We really couldn't talk about until we get to this point. And so remember, kinetic energy.
Hold on.
So far into the course, well, there's some subtleties of kinetic energy and potential energy that we really couldn't talk about until we get to this point. And so remember, kinetic energy is energy of motion. If an object has...
Listen to that. I'm totally agree. Energy in motion. But it doesn't have to be this motion you see. It can be in the form of a free body diagram. All right. So just because you don't see it doesn't mean that it's not present. I'm stating that this energy is there working, and engineers call it creep, right? And I'm saying creep is a kinetic energy. There is no damn equilibrium at that point if you got creep. If you have creep, you don't have equilibrium. All right. The moment you have creep, you lost equilibrium. But let's go on here and let's listen to my man talk.
Mass and velocity, it's got kinetic energy.
So it must have mass and velocity. Okay. Here we go.
But let's say that object is simply rotating. Does it have kinetic energy right now? Sure does. It's rotational kinetic energy. Instead of using its velocity, we're using its angular velocity. But a good question might be, does it have potential energy at this point? And the right answer is no. In a classical sense, an object can have potential energy because an object is isolated from the system. We have to add.
He says it's no potential energy if it's isolated from the system. This is where now his science is just you have to take leap of faith now into this. Well, because we can't isolate anything from the system. It's always connected to the earth. Everything, a system he's using is earth. So be careful of this double talk that people that call themselves scientists use. So it's earth, the system, earth. So he should clearly say earth, but he's going to say it. And that's why you'll see that I'm not trolling you, that I'm not extrapolating. I'm stating what he's stating.
add another object. So if I add the Earth to it, now it has potential energy. The Earth is producing this gravitational field.
Okay, the Earth is producing a gravitational field, which is not proven. It's not proven. All right, so you can't prove it, because for him to prove it, you'd have to take it out of Earth to show that it would not be connected, and you can't do that. We're on Earth, so you can never take anything out of here to try to prove its reaction on Earth. So he's doing something that can't be done. He's stating a hypothetical that can't be done. You can't claim that you're taking it off Earth and you want to use the example of it being on Earth. The two can't exist together. Let's do that again.
Because an object is isolated from the system. We have to add another object. So if I add the Earth to it, now it has potential energy. The Earth is producing this gravitational field, and there's potential energy stored in that baseball.
And what he's talking about is equilibrium. It's not potential energy. It's just a rock sitting on the ground. The rock sitting on the ground will do nothing besides the forces on the ground push back equally. Equilibrium, the rock will do zero. Now, if you want to really mess with your mind, well, then the forces are acting on it because the Earth is spinning. What forces is that? Wind force, rain, erosion. We're talking about different things now, but let's just go on. Bear with me here. Bear with me. I know I'm triggering.
So if an object is in motion, then it has kinetic energy.
So I agree that an object in motion has kinetic energy. But remember, I also state a free body diagram has potential energy. So you're creating it. So let's go back to his video, and I'm going to give you a couple more examples of this kinetic energy that you might be able to follow simply. My man is not here yet. Let's go.
It has to have mass and velocity. And remember,
he states that for kinetic energy to exist, it has to have mass and velocity. I just say it has to have forces. That this velocity, he's given it velocity. I'm stating it just for kinetic energy, just need forces applied to it. Excess forces, or forces that are not in equilibrium. Free body diagram. I'm just going to help you visualize this using what I'm in the background, what I'm going to show you here. Ultimately, it's going to actually be using similar to what he did. This is nothing right now. When he presses it in, he's created kinetic energy. It must only be maintained by the pressure of his finger. When he releases it, the kinetic energy that's there pushes back. There was no motion, though. No motion took place. No motion took place, but it was in a free body diagram. Forces were there, pushing back on his finger. As he released his finger, he did not release his finger faster than the pressure that was applied to it. It stayed with his finger. It stayed in equilibrium throughout his entire range of his pressure. Let's do this. Let's do it again. Watch his finger and watch.
The sheet metal.
He does not pull away faster than it presses on there. It stays in equilibrium.
Is not paper thin like it is today. And I want you to see where I'm pushing it in.
And think about that. His finger does not clear. And you think about a can that you squeeze. And I'm going to show it to you, and you're going to help understand it better. But let's go back to the rest of this video, and I'll jump forward to his, my favorite pet peeve is gravity. But that's not really what this video is about. But first off, kinetic energy. Well, we all have mass. Everything's got mass. An atom has mass. So this is redundancy, means nothing. You can cancel this out for everything in this formula. It cancels out. It's canceled out. There is no reason to mention mass here. Velocity is wrong as far as I'm concerned with kinetic energy, or we have to come up with another formula for kinetic energy, which means I have to change and make up another formula, right? Or I have to state that their definition of kinetic energy is wrong. So in theory, I'm wrong. If they're stating this is kinetic energy, all I can do is say, like gravity, kinetic energy is wrong if you must maintain velocity. I'm saying for kinetic energy to exist, you just must maintain forces. So if everyone states that kinetic energy must have velocity, I am wrong. I am wrong to try to change the definition of kinetic energy. I therefore must make up another one, which makes me kind of, reaching. Not reaching at all, because I would argue that no velocity is taking place at the point we see this guy pressing in on there. It's at equilibrium. It's static. And so velocity is not present per his velocity. And I'm going to show you his velocity. Please bear with me on this one. This is a tie into really good stuff. I'm going to jump in this video in a moment.
Remember, the equation for kinetic energy is 1/2 mv squared. If we know the mass and the velocity.
So most formulas, don't bother with the formulas, guys. Don't trouble yourself with formulas. All right, so the world exists without formulas. This is how we do it as engineers that state that this is how you can calculate it. Well, I already state there's a defect in saying velocity, so that means that this is wrong. I state there's a defect using gravity. So let's go here, because gravity can't be disproven because you can't show me something that's not subject to gravity. It's stating that everything's pulling on the earth. It's linear, meaning pulling in one direction. That means Newton's third law is wrong because it says everything has an equal and opposite reaction. Newton's law states this. Gravity has no opposite reaction. It just goes down to a center P, or what is it? What size? When does it stop? To the center of the earth, all the way around. So gravity's one directional. It doesn't work. And also keep Newton's third law and also the way physics work. Here we go.
Electric potential energy. But remember,
so I'm going to love this. So he's using the earth here, and let's go ahead. This is only going to last like 10 seconds.
Objects by themselves don't have potential energy. And
so he edited his video, and you can see him go over it. So I don't know. I guess he didn't like what he was saying, and then he edited to this part. He said objects by themselves don't have potential energy.
Remember, objects by themselves don't have potential energy. And let me.
So here we go.
Use a little PHET simulation to get at that. So if we take a pendulum and we lift it up on the earth, it's going to have.
Now he says the earth. Now he said the earth, right? So before he used the words system, but now it's the earth. So you can see he's playing with words because you can't prove something. So you just play around. So he should have said earth earlier, but this is what fake scientists do. This is junk. So watch what he says. If we do this, watch.
Have potential energy, which becomes kinetic and then becomes potential energy again. It's going to oscillate back and forth. But watch what happens if I get rid of the earth. Now there's no gravity, and I see.
Here's what he just said. He got rid of the earth to perform the subject on the earth, and he's going to say it stays there. Right then, it tells you just been fed bullshit. You just told me you got rid of the earth, gravity. And now you're going to perform the same test on the earth. It's not possible. The test can't be done even theoretically because the earth is a system, as he stated before. So you can't perform something inside a system and say you're not performing it inside the system. So he's double dipping, and I find this he triggered me 100%. He owns me at this point. So let's go ahead and do it.
Simply let it go. Well, that object is going to stay there. It has no potential energy.
How does he know that? He does not know that. Nobody in the history has ever been able to do this, to be able to lift an object up, state that gravity exists, and then let it go on the earth, and then state, look what happens when there's no gravity now. It stays here. Nobody in history in the world has ever been able to do this. You can't put it in a vacuum and do the same thing. It doesn't work. It's not the same thing. It's still in the system. It's still on earth. It's still subject to magnetic pulls and everything else in equilibrium. He's stating now that the weight of it, its equilibrium, doesn't exist in his mind. That this can only work because of gravity. That equilibrium doesn't exist. It's going to stay here because gravity keeps it up there, not because of equilibrium and this being an axis point, a hinge. I find that he made me come unhinged. Here we go. Let's do it again.
But remember, this doesn't have potential energy if it's in motion. We can only have potential energy if there's another object or another part of this system. Then it can have potential energy.
Is it a system again? Earth.
Could be gravitational. It could be electric potential energy. But remember, objects by themselves don't have potential energy. And let me use a little PHET simulation to get at that.
So objects by themselves do not have potential energy. Okay.
So if we take a pendulum and we lift it up on the earth, it's going to have potential energy, which becomes kinetic and then becomes potential energy again.
All it's doing here is a pendulum is finding equilibrium. Here's the load. Here's the counterforce of that when it, however, makes it goes up there. There's the energy, the kinetic energy left in it is this much. It can now swing using this hinge point, friction or whatever's in here, and it swings. And then it goes so far, again, the friction reacts, and the weight of it again is trying to find equilibrium. We all know where the equilibrium is going to happen, dead center here. That it's going to find equilibrium in line with the string or whatever this may be. the hinge point, etc. Here we go.
Oscillate back and forth. But watch what happens if I get rid of the Earth. Now there's no gravity, and I simply let it go. Well, that object is going to stay there. It has no potential energy.
Crackhead statement. You can't get rid of the Earth. You can't perform this theoretical or in reality. You can't do this. So this is, and he's stating it like facts, And this is the problem where I say this is fake science. This is hypothetical in a damn drawing. He can't do it. It cannot be done.
There's no stored energy because it's a single object.
And
Let me add the Earth again. Now we've added that potential energy back. Let's say.
All right, so triggered owns me. All right, so oil canning. Let's go to how this all tensions. What is gravitational potential energy? All right, so this is what that was dealing with. This is all junk. This is equilibrium again. He's holding this up. It's holding up. He's using his shoulder, his load, his weight. Ultimately, his weight at this point is holding this up. And the elongation is being held by his muscles in the shoulder and also in the forearm. Now, that's all that you're looking at. That's all you're looking at. Here's a friction point, a hinge point, and the weight wants to find equilibrium also. The weight wants to find equilibrium. There's nothing counterforcing it. There is no, this air around us, O2 around us, is not counterforcing it because the air is counterforcing also. Air underneath is also around here. So air is at equilibrium around this product. This weight is not at equilibrium, therefore it's like, say, let's call it 10 meters, 10 newtons, right? There is nothing pushing up against it at 10 newtons. It's off of its base. Nothing counterforcing it. Air is not a counterforce. This equilibrium is counterforced at this point by 10 newtons by this rope, or this, what I would call it, extrapolate as a rope or whatever, right? You put whatever in your brain, a wire, any damn thing you like. But it's being held by this man here, or person, this, what we call a person, or a shadow. That's all you're looking at. It's equilibrium. Anybody mentions gravity to me, punch him in the face. Pisses me off. I don't really want to punch him in the face. It's I don't have that that anger. It's a joke I like to show the extent of the frustration I have. All right, so that's all you're looking at. Equilibrium, baby. Everything's in equilibrium. So we come here to our buddy here, oil canning, and he's got it this way. And here we go.
Pushing in on that. And take for granted now, this is a 67, so.
He pushed there. When he did that, he racked this whole vehicle on the stands. The vehicle even found equilibrium coming back to where it was. Watch the whole vehicle rattle, shake here. Watch, here we go.
This out.
Everything wants to find equilibrium.
Because when you're working on a piece of sheet metal this long, it's very, very important.
When he does it, he puts torque on this, or even on the base, gets torque, and it finds equilibrium. And that goes all the way down here. Look at the whole thing right to shake, not just his dent. And it finds equilibrium. But it goes back and forth like the pendulum. It went too far when he released it. Then it came back. Watch it shake again, just like the pendulum thing. See how it rebounds? Those are the forces that are taking place here. All right, let's move on to, not that guy anymore. Anybody here? Oil canning. Let's do the oil canning part, and I'll terminate the video. So, free body diagram. This is, I want you guys to see the kinetic energy in the things we do to things, such as pressing on something, moving your toe, anything. It's mostly all kinetic energy. Potential energy to me is like, the sun coming up tomorrow is going to energize the, I just find potential energy just, why even call it energy? It's just, why do we have to say potential energy? It's just, it's what? Potential energy. We got stored energy. We got kinetic energy. I don't get potential energy. I don't get it. If you lift a ball above someone's head, you've got kinetic energy holding it, and they are part of a free body diagram. They're in the path, the load path of the free body diagram, like his finger was when it came back. And let's do that. So I want to give you a couple things about oil canning here. So this again, where you can come here. Oh, I want to back up a tab. So I want you to possibly look up oil canning, and you can see how it talks about elastic, buckling, etc. This is going to really help you with any of your metal deflection. And keep in mind that for example, when he's doing this, he can't figure out why. I mean, I love his stuff, his content. I follow the guy. I used to not like his cursing. I got used to it.
It's not paper thin like it is today. It takes a time to do it.
So I got advanced. Let me look at his video. I got advanced to 950 in his video. So he's going to be baffled by what takes place here because he's first explaining how oil canning and how you can heat it up and then bend it back. But then he's going to be baffled by why it goes in or out in this case. Watch. And you guys should be able to figure out why. So he's straightening metal, you know, all the body guys.
And now, by using our hammer and dolly, what we have done,
the skill set of somebody like him, they love metal being straightened by this and not by mud, by
back out
plaster.
And have made that a weld that we can grind down and do body work to.
Oh, I went too far.
Now what we'll do is we'll go ahead and move ourselves over.
Right here, sorry. So he heats it up. And what happens when you're heating it up? It's kinetic energy he's putting into this metal. It's reacting, and it's also going to have to cool down, so it's going to change it. So he's shaping his metal while it's still hot. When it cools, it then is going to take on as it's cooling, it's going to shrink. And that's more kinetic energy that it's going to resolve. He's creating tension inside his metal. So no offense, but this way of shaping metal is just is a wild card. And you're going to hear how he's going to be baffled about his wild card. Well, this is why. This angle here, this new metal here that he heated up has got a new profile in it has a new profile in its material hardening now because he put that heat on it. It's just a wild card. So in other words, this system of hammer welding, no offense to him, it's a wild card, ridiculous. Might be fun though. So here we go, listen.
So on this particular situation, since we have that weld there, it looks like this pulled out instead of went in. So I'm going to use.
It looks like it pulled out instead of went in. So you try to predict that it would go in. But that's not the way it goes. Each one of these created a new profile in this metal. A new profile in the metal. When he welded here, it hit the new profile and reacted as such. You know, it did its own thing plus the heat related to the area around it. And so you tell me, you know, he just put in a tensile strength that's probably higher than the metal around it, the 023 metal I think he used for welding. That created a path that probably created, if you can imagine it, as he put heat on it, it probably went there and went around like a cone around it. And so this is why it's a wild card for him.
Use my dolly on the inside.
Let's get 950 to say something.
And now, by using our hammer and dolly, what we have done, because on this particular weld, for some reason, it pulled out instead of went in.
See, so for some reason, it went out instead of in. There's always a reason. And in this case, he might have created the reason right here. And you're chasing your tail or something like this. Now, I'm going to go to the video. I'm going to show here. I want to show yeah, I'm trying to share the camera now. So, all right. So, oil canning. This is the can in equilibrium now. These are the bends in it, in this can. You're looking at equilibrium at this point. No creep, no gravity trying to push this to here. I could leave this here for 30 years and no gravity is going to say, well, I want to make this come to here. In gravity's format, this is overhanging here, so gravity wants to fold this can over. This can is in equilibrium. The air is inside of it, around it. Everything's in equilibrium with it. It will, until it will rust equally. It's no stresses in here that are not in equilibrium until I do this. Now I put this stress in here. As I do that, did I permanently deform it? Did I call permanent deformation? Well, I just gave away. Did I call permanent deformation? When I move my finger, will it stay where it is? No, but think in a free body diagram, I just put a force on there. a kinetic, and inside there's a kinetic force going on right now. It's pushing against my finger, whether I can measure it or not. It's pushing against my finger. I know that because when I release, watch, it comes back, and I can't remove my finger fast enough. If we could slow this down, I can't more than likely remove my finger fast enough for this to not stay with my finger as I press, as I load it. It's staying right with my finger. As I push in, it's equally pushing out, and I can't beat it. I can't beat it. It's equally in equilibrium, equally pushing back. This is what equilibrium is about, pushing back, right? This is Newton's third law, equal reaction, which I call equilibrium, right? So equilibrium, that's what you're doing there. So I'm trying to get everything down, and I'm going to change my channel's name. I think I said that to you guys, but slowly I'm going to change it to show everything that I'm teaching, which is hinging. It's a hinging right now, taking place in multiple places, which we call moments. It's for you to figure out where those hinges are taking place and to resolve them or not resolve them. But this load is pushing back on my finger. This in here is pushing back on my finger. This creates a force in my finger that must be maintained, or it will push back and fail. So right now it's in equilibrium with the force I put on it. If I started failing here, this would start pushing back and the reaction happens. So this is oil canning. And this is equilibrium also. I can't separate my finger fast enough to do that. Maybe I can use a high-speed camera. Maybe I can teach myself to move faster than this. In theory, I won't be able to, because this is the one that applied it. And so in theory, I would not be able to move away fast enough. That it's in equilibrium right now. All the way through that range. Through the range as I press on it. It's equally pressing back. Not one bit more, not one bit less. It's not giving me more forces back than I'm putting against it. And that's that. It's just simple as that. Let me switch back to the camera, oh, I guess let me see if I can do this. All right, so right now, I've got to look his name. Hold on. Mark Fisher is arguing with me on his side, arguing on my side. He thinks that the steel and the structure reacts the same as post-tensioning. That steel, post-tensioning just removes, is a replacement of steel. It is not. It is not a replacement. Steel reinforces the structure. Post-tensioning is an active force. It's an active being tension. It's an active compression in the member that counters this force. So watch when I press this in. If I were to add post-tension and stop me to be able to deflect this, I would, let's see, I'm just trying to think where I would put that. So it's deflecting there. I'm going to try to see if I can do this by putting a side force on here, a counter force with my hands in compression to see if it would stop it. So it stopped it to some degree. But because my load there, as I move to the edge, it becomes more deflective. Let's see if I try even more counter force. And ultimately I'd get to a arch, and now it becomes in compression and pushing things to the side. I lost it on that one. So the post-tensioning is not the same. It determines that, and theoretically, you figure out where the structure is going to suffer tension. And then you put where it's going to suffer tension. You don't allow it to go in the tension. You put compression on it with the post-tensioning. It's an active system. It's always working there. It's always pressed. It's always there working. It's holding. And you can load it now. And if you load it, it can hold it. But if this post-tensioning fails, then now you're at zero. Now you get failure. It's simple as that as far as post-tensioning, if you think of it that way. Or you figure out where it's going to fail in tension. You don't allow it to go in tension. You don't allow it to open up by keeping it in compression with the post-tensioning. Post-tensioning bars do not do not put a compressive moment on a structure, rebar, post tensioning bars. Apologies, post tensioning bars clearly do. Rebars, what I meant, does not put a compressive moment in there. So it's not replacing the steel. So if you can imagine, is what I need him to see is that it's not just here's a piece of number 8 rebar laying there, and instead we just happen to tension some metal, some wire, some rope, and that's now a number 8 rebar. No, number 8 rebar lying there does no compression. It's just a limp deal. It's passive, waiting to become active. It's just lying there. As you apply the load, the tension wants to happen, but the tension can't happen because it first has to try to make this rebar, when it becomes active at that point, the forces in the rebar and the bond of the concrete around it, the forces for it to still break, it has to elongate the rebar just a little bit or break the bond, and then you're going to get the tension cracks. So it's sitting there passively, just sitting there. That's the quick version of passive rebar, if you will, the way it's working, not the same as an active system as post-tensioning. It's active. It's active. It literally is there working all the time. Rebar is not the same. It is not the same. So hopefully you understand that. And I did give you permission to write because you are now triggered me to the point of saying, you know what, just post your comments. I can't read them. And so you see the way I'm acting, because I can't read them because I don't, this your way you're thinking is wrong. Let me you don't understand rebar and post tensioning, how the passive active system works. Now you're pretty smart, so I hope you won't be triggered by me presenting the way I did, and because we enjoy your comments, as many people state also. You make sure you're there. I think I'm screen sharing now. Let me confirm that. Good, I am. So Mark up here stating that Hooke's law only works on the elastic limits of the cables. No, Hooke's law works pretty much in all tension. Equal and opposite. That's all it amounts to. Equal and opposite. All right. So and if it's got different ends, I think you asked why is it different on the other end? Because it's not equal and opposite, but it is equal and opposite in relationship to that end. Okay. Well, elastic, right? But there's one more bump before you become plastic. After elastic, there's one more bump, increase and load and strength, and members before it becomes plastic, and failure happens after that. There's another bump, increase, even though it's past the elastic range. So let's quickly, the structure. So if as I just told you, it works. You just got to figure out where it's going to fail in tension, and then you make sure that your post tensioning resolves that before it could fail. That your post tensioning is such an extent that tension can't be created in the concrete, so you can't get failure. It's simple as that. It's theoretically as simple as that. Give a second. Okay. it was used as a substitute for structural steel. So here, right here. But in the deck, it wasn't used that way. It was used as a substitute for structural steel as assumption that stretch. So right, this is wrong. It's not how it's done. Structural steel and AC, they're different. They're not the same. It was not used as a substitute for structural steel. The thin deck, there was no way that I can think of that thin deck, the ratio you could put that much steel in it to keep it from deflecting with the length of it, the ratios. So post tensioning would have basically the only way to go here with this design, except for you could also use, more cables from the pier, but they didn't do that. It wasn't going to be cabled like that. So that's my position on that. I'm not going to. I guess I'll read the last one a little bit. Mark edits his stuff sometimes, so now I can't find it. Question: What was holding up the bridge? What was the support? Is this between the piers? It was the longitudinal post tension cables. They were the substitute for the structural steel. They were used in a way they were never intended to be. The design intent seemed to be to build a kind of web or mesh similar to welded wire fabric. Well, I see that's the way you see it. Okay. Did you just change this? It doesn't say edit it. Maybe you deleted it because you're allowed to control your stuff now, allow you to control it. But I thought you had a lot more than that a second ago. Yeah, and where's the rest of this one? What the heck? What's going on here? More comments? That's weird. Okay, yeah. So that's that. So all I'm trying to get you to understand with all this stuff is that there are forces in everything. There's an equal and opposite reaction. You have to figure out where that equal and opposite reaction is going and how you're going to resolve it. Is it also countered by an equal and opposite reaction? And is it on the backside of that? Is it also like a pyramid? Is it also now equal and opposite? Is it okay on the backside of that? And when they released number 11, they no longer kept an equal and opposite, and it found equal and opposite. It found equilibrium. So where are we going here? I'm going to look to see if you got any comments, and then I'm going to hocus pocus you. I'm out of here. Take care.